Hi everybody, my name is Asharaf Faraj and I'm a student in the National Center for the Distinguished in the Syrian Arabic Republic. Today I'm going to present a research entitled by the Riman Hypothesis, which is a research in complex analysis supervised by Mr. Habib Isa for the year 2016-2017. Let's start talking about a brief historical background of the hypothesis. Just to mention, the Riemann hypothesis is connected with a complex valued function called the Riemann zeta function, which I'm going to give its definition later on. Now, historically speaking, Leonard Euler was the first person to study the Riemann zeta function as a function of a real variable, and he was able to establish a tremendous result connected with the values of this function at even positive integers. But it was Bernard Riemann who first studied the function as a function of a complex variable and extended it via analytic continuation to the whole complex plane, with the exception of a simple pole at s is equal to 1. Bernard Riemann then made a conjecture about the zeros of this function, and it was then called the Riemann hypothesis, and it is not solved until this moment. The Riemann hypothesis, along with other 6 problems, were placed by the Clay Mathematical Institute in the list named 7 Problems of the Millennium, and the institute actually proposed a prize of $1 million for the person who solves any of these problems. Let's move now to talk about the problematic of the research. During my study of the Riemann hypothesis, a few questions started popping up into my mind. First of all, what is the Riemann hypothesis about, and what gave it such great importance? Second of all, what are the most effective equivalences for this hypothesis? Third of all, since it's a complex valued function, what are the most famous computational strategies used in calculating its values, and why are those values so important? Just to give a note, I'm also going to demonstrate 2 new equivalences for the hypothesis, which I derived by myself, and I've never seen anything like them in any other reference that I've already read. Now let's talk about the research plan. The first chapter is titled Generalities, the Riemann zeta function. I'm going to talk about the analytic continuation, the functional equation, and the values at integers of the Riemann zeta function. The second chapter is called the properties of the Riemann zeta function. In it, I'm going to talk about the zero-free regions and the statement of the Riemann hypothesis, Hardy's theorem, the zero counting function, and the great Vernon's universality theorem. The third chapter is called the computational strategies. I'm going to mention 3: the Euler-Maclaurin summation formula, Hardy's function, and Riemann-Siegel formula. The last chapter is about the equivalences of the Riemann hypothesis. I'm also going to mention 3 only, which are Lagrange's equivalence, Lie's criterion, and Volchkov's equivalence. Of course, at the end, I'm going to talk about the new equivalences which I mentioned at the beginning of the research, and conclusions. Now, first of all, let's begin talking about the generalities of the Riemann zeta function, and first of all, the analytic continuation. Now, the Riemann zeta function in its basic form is given by the relation zeta s is equal to the sigma of n is equal to 1 to infinity of 1 on n to the power of s, where s is a complex number with its real part being bigger than 1. Of course, the validity of this definition is justified by the integral test. Now, as we mentioned earlier, Riemann was able to extend this function to the whole complex plane, with the exception of a simple pole at s is equal to 1, and he was able to do that by defining it with the following relation. Of course, the derivation of this relation is shown in the full research. And as we can see, the function also has a pole at s is equal to 1 because of the term 1 on s with s minus 1. Now here I just presented 2 pictures to represent the difference in the real part of the Riemann zeta function before analytic continuation and after the analytic continuation. Of course, the left picture shows the real part of the zeta function before the extension, and the right part shows the real part of the zeta function after extension. Actually, it is very clear that both pictures are identical in the place where the re s is bigger than 1, of course with the existence of the simple pole at s is equal to 1. Now let's move to talk about the functional equation. Now, how can we find a functional equation for the Riemann zeta function, and how can we use it? actually an elegant and an extremely simple functional equation for this function can be found by noting that both sides of the earlier equation, which described the analytic continuation of zeta function to the whole complex plane, is symmetric under the change s to s minus 1, which yields the following functional equation. Actually, this equation will be of great interest for us in calculating many of the values of the Riemann zeta function at negative odd integers, as we're going to see later on. Now we're going to talk about the values of the Riemann zeta function at integers. Of course, the following result, which is shown in front of us, is due to the Swiss mathematician Leonhard Euler concerning the values of the Riemann zeta function for positive even integers. Of course, the b to k notation is denoting the even Bernoulli number of order k. Of course, I derived this relation in the research using the residue theorem. And of course, depending on the functional equation, another relation for the values of the function at negative odd integers can be found just by plugging the earlier relation in the functional equation. Just to give a note, the values of the zeta function at negative even integers are all equal to zeros. And of course, we're gonna talk about the zeros of the zeta function in detail in the next chapter. Also, the values of the zeta function at positive odd integers were not found at all, and we don't even know if these numbers are rational or irrational. Now we are going to move to the second chapter to talk about the properties of the Riemann zeta function. First of all, the zeros of the Riemann zeta function and the Riemann hypothesis. As we mentioned earlier, we said that the Riemann zeta function has an infinite number of zeros at every negative even integer. Of course, these zeros are called the trivial zeros of the Riemann zeta function, while on the other hand, the Riemann hypothesis is considered with the other non-trivial zeros of the function. It was also proven that the only area in the complex plane where we can find such non-trivial zeros is in the critical strip, which is shown in the yellow color in this following picture. Now here comes the Riemann conjecture, which states that all the non-trivial zeros of the Riemann zeta function lie on the critical line, which is shown in red in the following figure. Now we're going to talk about two theorems connected to the non-trivial zeros of the Riemann zeta function. And first of all, Hardy's theorem. The American mathematician Hardy proposed his theorem, which is considered to be one of the first theorems in favor of the Riemann hypothesis, and it states intuitionally that there are infinitely many non-trivial zeros of the Riemann zeta function on the critical line. Second of all, we're going to talk about the zero counting function. The German mathematician van Mangold was able to derive an extremely elegant formula for counting the non-trivial zeros of the Riemann zeta function on the critical line to a certain height d. Of course, the relationship is shown here in this slide. And just to give a note, a sketch of the proof of both the theorems is given in the full research. We're going to finish talking about the properties of the Riemann zeta function, and at the end we're going to mention Vernon's universality theorem. Just to mention, this theorem is considered to be one of the most outstanding properties of the Riemann zeta function, and it states intuitionally that the Riemann zeta function is capable of approximating any other analytic non-vanishing function in the region of the critical strip. Mathematically speaking, it might look like this. Now, just to say this mathematical expressions actually means that the lower density of the set of the vertical shifts in the argument of the zeta function satisfying the approximation relation among the real numbers is actually bigger than 0, which gives it a non-zero probability of existence, which by this way proves the Vernon's universality theorem. Now we just entered chapter 3, computational strategies. First of all, we're going to talk about Euler-Maclaurin summation formula. Just to talk about this summation formula at the beginning, the Euler-Maclaurin summation formula actually connects between the sum of the values of a certain function, of course at integers in a certain interval, and the integral of the function on the same interval. Of course, the following relations shown here are given upon applying the Euler-Maclaurin summation formula of the function 1 on n to the power of s, where s is a complex variable. Of course, this relation is considered to be extremely complicated and extremely complex, but it's still the most used one. Now, before going to talk about the second computational strategy, which is the Riemann-Stiegel formula, we will have to define something called Hardy's function. Of course, we all know that in any real valued function, in order to know the location of a certain zero, we will have to find values of the function in which it changes its sign, and by that the zero will be restricted in a certain interval, and we can keep doing that until we can find a certain appropriate approximation of the zero. But by the way, this technique cannot be used in complex analysis because there is no notation of sign in complex numbers. Now, Hardy was able to define a function which actually approximated the values of the zeta function over the critical line. It also helped us to find the locations of zeros of the zeta function because of its sign shifting, which we can use to depend the location of the zeros of the function. Now, let's talk about the Riemann-Stiegel formula. Now, this formula was used to approximate the values of Hardy's function, and hence to approximate the values of the zeta function via this formula. Of course, the derivation can be found in the full research. Right now, we're going to talk about the equivalences of the Riemann hypothesis, and we're going to mention only three. First of all, let's talk about Lagaris's equivalent. Now, this equivalent is considered to be one of the most elementary equivalents to the hypothesis, and is given by the relation sigma n is smaller or equal than hn plus e to the power of hn multiplied by the logarithm of hn, where hn is the nth harmonic number and sigma n is the sum of the divisors function. Now lies a criterion. Now this criterion is also supposed to be a simple one in a attempt to try to prove the hypothesis, because it is considered with the positivity of a number of terms in a certain sequence, which is defined by the relation showed here. Now, Volchkov's equivalent, in my opinion, is also one of the most elementary equivalents to the Riemann hypothesis, because it's given in a shape of a double integral which can be manipulated easily. Now, the Volchkov equivalent is given by the following relation. And of course, the conclusion of the equivalence of Volchkov to the Riemann hypothesis is given fully in the research. Now I'm going to finish talking about my research and giving some of my equivalences. Now the first equivalence. The first equivalence that I found was very connected and it derived from Lagaris's equivalent. It is in the shape of the following inequality given by this relation. Of course, the idea of this inequality is extremely simple. It's just that I divided on n to the power of x and summed both sides from n is equal to 1 to infinity. But this relation or this equivalence can be yet used to derive other equivalents which might be easier because of the ability to manipulate the values of the zeta function right here. Now the second equivalence, which is considered to be far way easier than the first equivalence, was derived based on a double integral representation of the Riemann zeta function, which was also performed on the unit square. Of course, it is given by the following relation, where the gamma notation is known as the ordinate of the non-trivial zero of the Riemann zeta function. Of course, both proofs of the equivalences are given in the full research. Now the conclusions. At the beginning of the research we ask three questions. What is the Riemann hypothesis and why it is so important? Now, actually, as we saw, the Riemann hypothesis is a certain conjuncture connected with the non-trivial zeros of a certain complex valued function called the Riemann zeta function. Why it is so important? That is because by proving the Riemann hypothesis, we would have proven millions and millions of other theories which actually depend upon the truth of this hypothesis, just to mention few: Goldbach's conjuncture and Chen's theorem. Now, what are the computational strategies used in this in computing the values of the Riemann-Zeta function, we said there were two: the Riemann-Segal formula and the Euler-Maclaurin summation formula. Why are the values of this function so important? That's because they appear in many different fields of physics, in quantum physics or in quantum gravity or other new theories which would change the world. And at the end, we also wanted to know what are the most effective equivalences in trying to prove the hypothesis. I actually found that Lagarce's equivalent, Lazar's criterion, and Volskov's equivalent are the three most elementary equivalents to the Riemann hypothesis, because we can manipulate their shapes extremely easy, and we can yet derive other equivalences from them. And at the end, I also showed or demonstrated two new equivalences, as you guys saw earlier, depending on Lagarce's equivalence. Of course, my next step is to try to improve the bounds and to sharp the first inequality to give a more effective equivalence of the hypothesis in my quest to try to prove this amazing hypothesis. Now, here are some of the references that I used in my research. And finally, thanks for listening.